Okay, everyone, welcome to the 2022 hottest event for junior researchers, part 1 of 2. So our first speaker today will be Thibaut Benjamin, who is a postdoc at CEA, and he'll be talking about some work he did while at École Polytechnique on CaTT, a type theory for weak omega categories.
Yeah, thank you very much. Today I'll present this type theory, which is called CaTT. And it was introduced by Finster and Mimram, and they are my PhD advisors. So I did my PhD with them on this type theory, and I'll mostly present the type theory itself and how it works. And if I have some time, I will give 1 or 2 words about what I've done about it. But I can't promise anything because it gets some time to get started into understanding the theory itself. So, sorry about that. So yeah, now I'm working in quite a different area, and I do some runtime verification of C programs for the software pharmacy, and I'm kind of planning to go back to more categorical and algebraic stuff later. So first, to understand this, I want to talk to you about the HoTT and the groupoids and Brunerie's type theory. Because you might, so obviously you know all about HoTT, you know most probably about groupoids, but you might not know about this type theory proposed by Brunerie, and it's quite important if you already know HoTT to understand that, then to understand CaTT, which is the next step. So, well, first, I'll start with something everybody here knows, the iterated identity types in HoTT. They give the structure of a weak omega-groupoid to any type. So that's all well and good, but what Brunerie has done is he abstracted out this structure, and instead of defining HoTT and having this entire machinery to get the weak omega-groupoid, he gave less powerful set of rules, but also a way more minimal set of rules to define this algebraic structure. So what does it look like? So you strip off everything except the identities, because that's what you want to describe if you want to have weak omega-groupoids. And a context then only looks like something like this. So here you see you have X of type star. Well, it's just a generic type, because if we want to take identity, we have to take the identity of something, but it's just some sort of type so that we can take identities. So here I just chose X, Y, and Z of this type star, which is just any type really. And then I can say that I have an equality between X and Y, an equality between X and Y, another one, and so on. So I have all the iterated equalities, like in HoTT, but I don't have anything else. And so these contexts, we can think of them as some sort of description of an equality situation. And the technical term for that is computed for weak omega-groupoids, but I won't go too much into that. And I'll draw it as this nice diagram where I have X, Y, and Z here. And I just draw the equalities between them as they are indicated in the context here. So that's the first thing that we can describe, but we don't have any structure yet. So now we are going to add some structure to the theory. And for that, we'll add I say composition, but it's actually composition and axiom, and they're kind of, they are mingled, like they are mixed. You can't really separate them in this theory. So in HoTT, how do you get the composition and all the axioms that give you actually the weak omega-groupoid? Well, you use the recursors that you have for the identity types. But here we don't have recursors. This is too complicated. Recursors are like for you define the family, then you define the term for every stuff that you can have. There is some quantification. It's very complicated. And instead, we just define some terms by hand. So instead, we define the compositions. So I say compositions and axioms. Really, you may think of them as very similar. And I'll give you just a few examples. I don't explain to you how to define them, because I just want you to picture what you can do with it. And this will ease our way into CaTT, and then I'll show you in CaTT how it's done, and I'll show you with real examples. So for instance, we can derive this term here. So here I've written a context, which if you parse it, you see that it's this equality situation here that I've drawn. And from this context, you can define C of f and g, which has type x is equal to z, and it's just, well, in groupoid terms, it's what we call the composition. In equality terms, it's the usual, how's it called, transitivity of equality. But we don't use the recursors for that. We have rules that allow us to derive a term like this. Same thing for, so that's like a composition, and there's also an axiom. So I take the associativity for as an example of an axiom that I can require. So here I have a much bigger context, but this is actually just this here, this down there, this equality situation that I've described. And from there, the rules of the theory allow me to derive a term, which I call A of f, g, and h, which says that the composition associated this way is equal to the composition associated that way. So really, again, I have a theory, and then I have the rules of the theory that allow me to define such terms. And what's interesting here is only from term introduction rules and type introduction rules, I describe shapes and an algebraic structure on these shapes. And now I'm going to do the same, but for categories. So this is the theory CaTT. And so the way I want you to think of it is exactly as Brunerie's type theory, but we replace weak omega categories, weak omega groupoid with weak omega categories. And what does that mean in terms of equalities? Well, we're not interested in equalities anymore. We're interested in some sort of a rewriting relation. But it's not a usual rewriting relation. It's a sort of a proof-relevant rewriting relation where you can iterate and go on rewriting relation on level 1 and then on level 2, level 3, the same way we do in HoTT. So all the levels are directed. All the levels should be understood as defining some sort of rewriting. So now, exactly like in the case of Brunerie's type theory, the contexts are arbitrary rewriting situations. So the technical term, again, is computed for weak omega categories. I'll talk a bit about that at the end of the talk. And we can define compositions and axioms for those the same way we did for Brunerie's type theory. And with the description of the context, so the description of the types really, and the description of the axioms and compositions, which are term constructor, we get an algebraic structure, which will be the algebraic structure of weak omega categories. So first, let me show you what context may look like. So in Brunerie's type theory, we had equalities. So just replace them with rewriting relations. So here I've taken the same context, except that I've replaced all the equal signs by this arrow sign to indicate that they are directed, but it's exactly the same. Formally, it's the same. And I'll draw it the exact same way, except that I replace the equal relations by arrow relations. And here I draw a two-dimensional arrow to signify that it's a two-cell. So actually, since the beginning, I've told you that contexts look like this. They may be more general, but we cannot see that yet because we don't have term constructors. But later on, we can put term constructors inside the context. So that's why they are actually computed. If you just look at diagrams like this, where you don't have any term constructor, so the one we can build for now, are just globular sets. So among these globular sets, among the contexts that we can build, I'll be very interested in pasting schemes because these are the ones that will tell me how to define omega categories. They are very important for me. And intuitively, they are the context that describe a rewriting situation, which is completely unambiguous. If I present you with this rewriting situation, you know exactly what you should do and how to get a single non-ambiguous thing out of it. So for instance, if I have this one where I have two rewriting steps that can compose, well, you can just compose them. If I have this situation here where I have complicated stuff, but there's essentially a single thing that you can do. You don't have any choice. You can just follow these two inside the composition in there. And that's just the only thing that makes sense. On the other hand, if you have something like this, oh, sorry. I want to go back. Thank you. If you have something like this, this is rewritable. I mean, you could go here and then go there, but then you might as well go once again, and then you don't know how many loops you have to do. So that's ambiguous. Even though you can sort of say this defines a rewriting operation, it's completely ambiguous. You don't know which one it is. And this one doesn't define the rewriting situation because there's a hole here, so you can jump from here to there. So that's these are the two obstructions actually that you'll find, whether there's a loop or whether there's a hole. And so the nice thing for us is that you can recognize algorithmically which contexts are pasting schemes. And that's very useful if you want to define it as a type theory, as a proof assistant, because then you can implement this algorithm to check whether a context is a pasting scheme or not. And I'll show you that in a bit. But first, I just need to briefly explain to you how we get the rules for CaTT. I won't detail the rules because they are quite complicated to state, but intuitively they make a lot of sense. So I'll just give you an intuitive sense of what they do, and I'll illustrate with some real derivations. So the rules for composition and axioms, they express the idea that the space of all composites of a pasting scheme should be contractible. So it's not exactly clear what contractible means, because remember, we're not in HoTT. We don't have equalities, but we have rewriting relations. But contractible in a sense which would be compatible with rewriting relations. So basically, I'm just saying in a weak way, in a like weak-friendly way, that the pasting schemes have a single thing to do with them, but so in a weak setting, you would say that the space of composites is just contractible. So this gives rise to two rules. The first rule is the rules that generate the operations in the weak omega category, is that every pasting scheme has a composition. And the second rule, which enforces the uniqueness, but the uniqueness in a weak and coherent way. So it's quite subtle. It's not obvious how to do that, but it states that any two compositions of the same pasting schemes should be related by a higher sum. So if you follow this rule carefully, then you get uniqueness, but you get existence and uniqueness, but uniqueness up to higher cells in a coherent way. So that's a very, very powerful idea. And this is why it gets a bit tricky if you want to detail the rules. And instead, I'll just show you a live demo. So I guess now I'll change my screen and I'll show you the implementation of it, and I'll toy around with it so that you can see how it works and get a feeling for yourself. So I'll just stop sharing for, yeah, and I'll share the other screen, which is here. Share. So now you should see it. So this is my cheat sheet, so you should not look at it. So first, I'll show you the first rule. I'll illustrate the first rule, which is the composition. So, oh, sorry, I did something unintended. Yeah. So the composition, this is just a commentary. So that
can you increase the font size?
Oh, yeah, I can. I did something so that no. Zoom. Is it better?
Yeah, much better. Thanks.
Okay. Great. So the composition, well, I'll just, first I type co. Co just says that I'm about to introduce a new, we call them coherences. So it's either a composition or it's an axiom. We don't specify them, but basically a new recipe to build higher cells. Then I'll give a name. So I'll just name it com because it's a composition. And then I have to give a pasting scheme, which is the pasting scheme that characterizes this coherence. So here I take X and Y, which are of type star. Sorry, this is a Y. And then I take F, which is X to Y. And you might think that it's a bit weird that I'm writing in this order, because I'm just describing, basically I'm just describing F and G, which are two arrows, which is F and then G, which goes behind. So two composable arrows. So why did I write it in this order? Well, just the way we implemented it, in order to recognize pasting scheme, we ask them to be in a very specific order. I won't get into all the rules so that they get recognized, and I think we could just have a smarter algorithm, let's say, to recognize pasting schemes. So this is not very important. This is just implementation detail, let's say. And then, but so here I'm in the situation where I have X and Y. I have F, which rewrites X into Y. Then I have another Z, and I have G, which rewrites Y into Z. So I can just rewrite X into Z, and that's the composition in weak omega categories. And that's also what you would call the transitivity of rewriting, let's say. So I can just run cat on that. So if I do, here you see that I have the compilation running, and it says that let comp is something, and it's defined. So defined means it successfully defined it using the rules of the theory. So this is the illustration of the first rule. I give you a pasting scheme, and I give you a way to compose them, and it produces me a term that realizes this composition. Now I can illustrate you the second rule, which was, I give you a pasting scheme and two different ways to compose it. And I give you, and it produces a cell relating these two different ways. So co, again, states that I'm defining a new recipe. I call it ASOC because it's the associativity. I'll just copy paste this context here because it's just an extension of that. But now I'll take a W and a third arrow, which goes from Z to W. And what should be the result? Well, if it's the associativity, you can probably guess it. So it goes from the composition of F with the composition of G and H to the composition of F and G with H. Let's try this out. And yeah, as you can see, ASOC is also defined. So this is the second rule. Now I took a pasting scheme and I took here, this is a first way to compose my pasting scheme. And this is a second way to compose my pasting scheme. So I just want you to know that here I call comp with only 2 arguments here. When I wrote it like this, it might seem that comp has 5 arguments, but I can infer which one can be inferred. So I know which one can be inferred, and it's completely automatic, and there's a general theory of which one you can omit and which one you have to explicitly state. So you don't even need, when you write this, to put like curly braces or whatever. It's not even needed. It's completely automatic. So this is all well and good. I was planning, how much time do you have left?
3 minutes.
Okay, so very quickly, I'll show you the identity. Sorry, it should not be. Because the identity is an interesting case. It's an instance of the second rule as well, the one which given a pasting scheme. So here my pasting scheme is very steady. It's just a single point, and I have a way of composing a single point, which is just the point itself, and another way of composing the single point, which is again just this point itself, and I can relate these 2 things, and this produces me the identity. If I had more time, I could derive the unitality left and right unit of the identity. But now I have some time to show you some more interesting things, let's say. So now, let's say I want to show something in a context which is not a pasting scheme. This is also doable, but now I'll change the keyword. It's now let, and I'll show the square of an endomorphism. So I take X, which is an object, and F, which goes from X to X. So now this is not a pasting scheme. And indeed, I could show the square, but I could show the 3rd power, the 4th power of anything. But now I want the square. So I can just define it in terms of the composition. Remember, I just defined the composition. So this is just comp of F and F. And if I compile it, you see that it's defined and it's of type X to X. So this is really the squaring of the endomorphism F. And so how do you achieve that? How do you achieve defining something in a context which is not a pasting scheme? First, you have to unravel it so that the context is a pasting scheme. You define a coherence in that, and then you apply this coherence back in your weird context. So this is how you can do that. And I wanted to show you 2 things again. One is just a nice little trick that we have done. So sorry, I'll just take this one again, I guess. So I just want this actually. So here I take F, which goes from X to Y. I take G, which goes from X to Y again. I take H, which goes again from X to Y. And now I'll take 2 cells. I'll take A, which goes from F to G. And I'll take B, which goes from G to H. So now it's like two cells that compose nicely, that go one after the other. And I can write comp of A and B. And if I do that, what happens? Well, it does accept it. So it should feel to you that this shouldn't work because I haven't defined the composition of two cells. I've just defined the composition of normal cells. And if I apply the composition of normal cells, normal one cells, it shouldn't be applicable to two cells. Well, actually, there's so this is something I have done during my thesis. It's a nice automation mechanism where it says, well, it's true that I haven't defined it on two cells, but I can suspend this thing that I have defined here. And here I'll replace that with, let's say, 0 to 1. So 0 and 1 are just formal arguments, okay? I'll replace that with an arrow from 0 to 1 everywhere. So this is what's happening internally. I'm not doing it actually. And I'll define 0 and 1 before. And I should generate that actually so that the composition is usable. So internally, when I use the composition previously defined, it generates this term here instead of the one I had defined exactly. And it uses this term instead of the one I had defined before. Okay, so I'll just come back because otherwise it will be very happy. And a final thing is something that you can do, for instance, in a context that is not a pasting scheme, because I told you that I showed you contexts which are not pasting schemes and not globular sets, which is an actual computed. And I'll call the square of identity, for instance. I take X, which is an object, and now I take, let's say, A, which goes from the identity of X to the identity of X. So A is now a cell whose source and target are themselves constructed terms, not variables, not mere variables. It's a cell above the identity of X. And I'll apply comp of A and A. So now I'll use the suspension that I've demonstrated just before. I've showed you just before how the suspension works. So I'll use that again. And I use it in a context which is not even a globular set now. It's an actual how is it called? Computed. And if I do that, you see that it accepts it as well. And yeah, I think that will be all. I have a lot of different stuff defined in this type theory. Most notably, I have a Ekman-Hilton morphism definition, which is quite complicated. And you can go as far as you want in the theory of weak omega categories with this type theory.
Okay, thank you. Let's all silently thank the speaker. And I'll stop the recording.